we would accept of being wrong when rejecting the null hypothesis. He suggested 5%, but without a basis for his decision. Now, more than 70 years later, we are amid an increasing concern about the usefulness and the problems created by the incorrect use of the methodology and interpretation of hypothesis testing. But why do we need statistics, and is it not enough to present the data as it is collected, and what is all about scientific method, statistics, and epidemiology? We will analyze the basic concepts and then center today's presentation on analyzing the recommendations regarding the suggestion to abandon the use of p-values. First of all, without statistics, the amount of data in scientific investigation would be impossible to manage and understand. To make the data manageable, you first classify them to avoid getting lost. Then you apply the basic rules of probability. After classifying the quality of evidence, we proceed to make predictions and thereby make decisions regarding the diagnosis, prognosis, and treatment of patients. So we know that the use of statistics is to cope with variability and the large amount of information that comes out of every clinical investigation. We know that we are not able to study a universe, say, the people with high blood pressure in the world or in my city, and we have to take a sample, which we expect will be representative of the universe it comes from. But no matter how accurately and precisely we try to take that sample, Albert Einstein reminds us that the bias will always be present. In this regard, we hope that the sample will be efficient and the risk will be small if we accept the sample values as representative of the universe they come from. As shown in the Mayo Clinic proceedings, in 10 years' time, up to 62% of the published studies will have their conclusions reverted or inconclusive. There are many causes for some research not standing the test of time, and very often it's the poor quality, as has been mentioned several times by Ioannidis. As Robert Lee Hodges mentions, a big problem is giving too much importance to statistical significance and presenting the data as absolute truths of immediate application, when many are low-quality sponsored studies and the results can have statistical significance but not clinical importance. The phishing of P is the misuse of data analysis to find patterns that can be presented as statistically significant, thus dramatically increasing the risk of false positives. The phishing of P has become a modern sport, stimulated by the lack of methodological knowledge of journal editors and other decision makers about the quality of research studies and the selection of those to be published. This is an example of a result produced by data dredging, showing a correlation between the number of letters in the contest Scripps National Spelling Bees winning world, here in red, and the number of people in the United States killed by venomous spiders, here in black. The correlation is almost perfect, but clearly enough, nobody can claim a cause-effect relation of these parameters. Association does not mean causality. Chanticleer, the rooster in Edmund Rostan's novel, realized that the association was perfect. He sang and the sun rose. So he convinced the hens that his singing was what made the sun rise. But everything collapsed the day he fell asleep, and the hens saw that already the sun had risen. The rules began with Sir Austin Bradford Hill in 1964. They have evolved to the Evans criteria, but the foundations remain the same. Statistical significance refers to the risk of being wrong when rejecting the null hypothesis. When many hypotheses are tested, it's virtually certain that some will be reported to be statistically significant, and almost every data set with any degree of randomness is likely to contain some spurious correlations. Researchers using data mining techniques can easily mislead the readers by the use of these results. Let's review a little more the reason to use inferential statistics. If we were all the same, it would be boring. But knowing one individual would be enough to know all of them. But variability is the norm. So we have to observe the dispersion and calculate central tendency and variance values. That gives us some idea of the group's characteristics. To study a variable, we have to define the universe from which we want to know its parameters, which are obviously unknown, and we take a sample. With a probabilistic sample, we calculate some statistics, and with them we try to estimate the parameters' values. Statistical significance refers only to the probability of the sample data correctly reflecting the universe data. As shown in these diagrams, the distribution in the bottom graphic shows a large dispersion, the green line. By increasing the sample size, upper graphic, the dispersion will be reduced and have smaller confidence limits, and many differences, although remaining the same, become statistically significant. Compare the confidence limits of both graphics and the positions of the high tail of the lower values distribution and the low tail of the higher values. In the upper graphic, they are separated, and in the bottom one, they overlap. Although Fisher left open to experimenters the choice of the risk level for the rejection of the null hypothesis, in the following decades, 5% has been the reference to decide on statistical significance. But along that road, it has wrongly been used to decide on the importance, quality, and applicability of the investigation, and often used in a fraudulent way. Remember, p-values do not measure the size of an effect or the importance of an outcome, and by itself does not provide a good measure of the evidence. Most conclusions with p-values slightly below 5% are probably false. If so, the postulated associations and treatment effects do not exist. When studies are repeated in similar or stricter situations, most of the time the results are not reproduced. Even among those statements that are true, a small effect size does not have significance for decision making. There are some authors that warn us about the need to fully understand what statistical significance is. There is a key article published in 1995 where Donald McCloskey reminds us, as I have already tried to show today, that P is a probabilistic calculation of the occurrence of an event. If the results of the sample are an efficient estimator of what happens in the universe, and we can't speak of certainty. In addition to this, in our profession we have to differentiate the statistical significance, p-value, confidence limits, type 1 or alpha risk, from the size of the effect and the clinical importance and applicability of the findings. We should not be interested primarily in the question, how likely are these results if the null hypothesis is true? On the contrary, we should be interested in the question, how big an effect is there? As we saw, statistically significant values can be obtained by taking very large samples, even if the effect is small and without clinical significance. With this in mind, what is the author's reaction in view of the results of an investigation? In this table, we can see that a clinically important difference that reaches statistical significance, as shown in box A, pleases the researcher, for they facilitate publication. Unimportant differences or effects that do not attain significance should be okay. Box D. The annoying important differences that were significant, box C, indicate that too large a sample was obtained, but they are used to push medications and indications beyond the real value. Further, in box B, if a difference was not significant, but the investigators consider it as important, they conclude that the sample was insufficient, even if the sample size was calculated in advance of the investigation, and call for further research with larger samples, until one reaches statistical significance. This is a crazy use of the concept. In conclusion, unimportant differences that turn out to be significant are annoying. Important differences that fail statistical confirmation are truly depressing. This schizophrenic nature of the interpretation of significance greatly reduces its value. The concept of statistical significance has to be revised to the basics of what is the definition of solid evidence, as do groups like Cochrane, Appropriate Use, and Clinimetrics Corner. Defining this, we could proceed to analyze in depth the redefinition of statistical significance. John Ioannidis, whose aims are defined by himself as to improve research methods and practices and to enhance approaches to integrating information and generating reliable evidence, comments on the proposal to lower p-values from 5 in 100 to 5 in 1,000, or even lower, as other sciences like astronomy already do. The following are some proposals to reduce the degree of misinterpretation of p-values and its misuse. The first is to lower the p-value threshold, because it has been observed that with a risk of 5%, many studies are never replicated. It would be of some utility to show the actual value, because to say lower than 0.05 includes many potential values. Focus on effect size, the main objective of the investigation. Show the distribution's confidence limits. A few have gone as far as saying that p-values are useless. But what we have to do is disseminate its proper interpretation. We have to promote the study of science, and in particular biostatistics and clinical epidemiology. The main objective is to assess the size of the effect and analyze the results in depth, including the original values and not only the author's statements. At the same time, we have to show the biases and how some people lie with the statistics. Finally, Bayesian methods are very useful but require a deeper knowledge of statistics and probabilities. Anyhow, its use is increasing, and at least we have to understand its fundamentals. Do we need to be mathematical experts to understand the concepts of probability? Most calculations are done by computers, but we have to know if the chosen statistical method was appropriate and what is the true meaning of the results. We will use the contributions of Sir Isaac Newton, Gottfried Leibniz, and Leonhard Euler, who paved the road to understand calculus. The late German physicist Hans-Peter Dürr, on talking about the paradigm's shift, tells us that the relationships in nature are complex, and that the whole is more than the sum of its parts, that we are in a reality ruled by complexity, and we can no longer allow any reductionism. Does this scare you? For many doctors, it can be seen as an immense effort to be prepared on issues that are not familiar to us. The goal seems impossible to achieve. Einstein saw more than a century ago that changing a paradigm will be a difficult task. But if the sorcerer bought himself a stethoscope, we too can progress. If you decide to get prepared in science, please accept for some time the loneliness of knowledge and abandon the comfort of being part of the flock.